In this video, we will learn about dimension reduction, which is popularly used in AI modeling. As mentioned in the K-fold cross-validation video, the process of building an artificial intelligence model involves dividing the entire dataset into training and testing data. We train the model using the training data and evaluate its performance by testing it with the testing data. Generally, image and text data have a large number of features, which can be thought of as many X values. The number of these features is called the dimension. In the case of the data shown in this slide, it is represented as a n by p matrix, which means that there are p features and a total of n data points. However, when the number of features is too high, meaning p is large, there can be several challenges in building an artificial intelligence model. Firstly, not all features have an equal impact on the outcome, so there are certainly unnecessary features for constructing the AI model. Moreover, when it comes to data, visualizing it through graphs or other means is more efficient than dealing with numbers. If there are only two features, a two-dimensional graph can be easily created for visualization. However, as the number of features increases, it becomes more difficult to visualize the data. Furthermore, having a high dimension means dealing with a larger amount of data, which in turn leads to a more complicated model and significantly increased analysis time. As shown in this slide, let's say that the original dataset has p features. If we can reduce the number of features to a smaller number, k, we can overcome the challenges we discussed earlier. In other words, the number of features represents the dimension, so reducing the number of these features is known as dimension reduction. This process is widely used in the construction of AI models. For example, let's suppose that we have data representing physical body characteristics, and it includes information about height in 3 different units: millimeters, centimeters, and meters. Using only one unit, such as centimeters, would provide the same information. However, it would triple the amount of data. Furthermore, this table shows the scores of biology, physics, and chemistry. Instead of representing scores in these subjects separately, summarizing them into a single subject called science can help with data analysis and result interpretation while maintaining the characteristics of the data. In essence, the key aspect of dimension reduction is to decrease the number of features while preserving the important characteristics of the original data as much as possible, as there is a potential loss of information during the process of reducing features. Dimension reduction methods are divided into 2 categories: feature selection and feature extraction. Feature selection is a dimension reduction method where only the most relevant features for a given task are selected from the original high-dimensional data. In other words, unnecessary features are removed, and only the features that well represent the characteristics of the data are retained. To illustrate this, imagine there is a box containing balls numbered from 1 to 100, and we choose balls number 1, 50, and 100. Similarly, in the context of feature selection, specific features from the original data are chosen without any transformation. While the interpretation of the selected features is straightforward since they are directly from the original data, a drawback is that the interrelationships between features are not taken into account. In the example shown in the previous slide, among the 3 features representing height, millimeters, and meters are removed, and only centimeters are selected. This exemplifies the concept of feature selection. On the other hand, feature extraction is a dimension reduction method that transforms the original features into new features that combine the original characteristics in a way that preserves the maximum amount of information. Unlike feature selection, feature extraction does not directly select the original features, but rather transforms them into new features. To illustrate this, imagine putting 100 metals into a container, subjecting them to a chemical reaction, and creating a new alloy. Then, we select alloy number 1 and alloy number 2. This analogy helps to understand the concept of feature extraction. In the example shown in the previous slide, instead of representing 3 subjects separately, biology, physics, and chemistry, they are combined into a single subject, science, using this kind of a function. This represents feature extraction. The transformation of the three subjects into a single science subject using a formula implies that the interrelationships between the three subjects are taken into consideration. Therefore, one advantage of feature extraction is that it considers the interrelationships between features when reducing dimensions. However, a drawback is that the interpretation of the features is not as intuitive since we are not using the original features directly, but rather the transformed features. Popular methods for feature extraction include principal component analysis, PCA, and linear discriminant analysis, LDA. Before introducing PCA and LDA in the upcoming video, let me briefly explain them. Data used for training artificial intelligence models consist of X, representing the features, and Y, representing the labels or classes. Therefore, data that includes both X and Y is called labeled data, while data that only contains X is called unlabeled data. Supervised learning refers to training an AI model using labeled data, where both X and Y are available. On the other hand, unsupervised learning refers to training with unlabeled data, using only X. PCA belongs to unsupervised learning, as it utilizes only the X data for training. LDA, on the other hand, falls into supervised learning as it uses both X and Y for training the model.